Hello, everyone, and welcome to the Late Night Statistics Podcast, brought to you by Slagle's Mathnasium. This is going to be a little different as I'm recording upstairs today due to the infant who is currently sleeping in my recording studio. It's pretty inconsiderate of him. Anyways, let's go ahead and get started. Unit 3 was on bivariate data. And really what bivariate data means is you have two variables being measured, and they're usually data points that are linked together. Usually because it's one person and you're measuring multiple characteristics or one entity with data that's being grouped. So really, statisticians collect lots of data about one individual in the study and look at lots of comparisons between variables, but we're just going to all of those are really just looking two at a time. So let's go ahead and get started. Yeah, so I took the old data from our height and arm span data from semester 1, so that's what we'll be using to talk about comparisons today. Let's go ahead and move forward here. Before we begin, we need to remember if you have two variables in a study, then you need to be able to distinguish which one is X and which one is Y, because it kind of makes a difference. So in terms of how we structure our graphs, let's go ahead and highlight this and kind of shift her down a bit. Typically with our graphs, you're going to see a horizontal and a vertical axis. And usually the explanatory variable goes on the horizontal axis. Explanatory is horizontal, or this is our X variable, and then or the X-axis as we're used to calling it, and then we have our response variable that goes on the Y-axis. Okay, so response or the vertical axis. So how, when we look at a situation, how do we tell what we're trying to use to predict the other? Which one goes where? And I think you guys are probably going to have pretty good intuition on this, but basically, let's look at the first example: the yield of mint crop in bushels and the amount of rain in a growing season. Okay, so typically, we might call this the dependent and the independent, but basically it's all about which one causes a change in the other. And also, a lot of times it's, kind of which one do we have control over in a study. In neither of these cases we do, because they're, observational studies. We do not have control over the rain. We don't have control over the crop yield, so on and so forth. But I think you guys can probably see here the explanatory variable is going to be the one that's going to create a change in the other. So the one that gets changed is the response variable. So basically, the amount of rainfall kind of has control over the mint crop. So in that case, I'll say rainfall in, typically you want to include a unit in inches, is going to be our explanatory variable, which means our response is yield of mint crop. And the unit there is in bushels. Oh, what a fun, joyous measurement system we have. Okay, next one: the number of text messages sent and the number of phone calls made by a sample of students. Okay, if you're looking at text messages and phone calls, is there any one that necessarily creates a change in the other? Is there any order that really happens, or a hierarchy of things that are happening? And the answer is really no. So for this one, we can just kind of say, in this case, you could use either variable as explanatory, as one is not dependent on the other, or vice versa, right? So phone calls is not dependent on text messages and vice versa. All right, that's looking pretty good. All right, let's cruise on. Make a scatter plot to display the relationship between two quantitative variables. So after you have established, your height is explanatory and your arm span. So with these height and arm span, it's not necessarily, they're both just measured characteristics. There's not like one dependent on the other necessarily. They're both just, either one could be your explanatory variable. I'm using height as our explanatory variable because typically arm span is one that people aren't familiar with and might be familiar with their height. So what I want you to do here, I'm fairly confident everyone is going to be able to plot these points. That's all it is just plotting points on a graph. So what I want you to practice is I want you to practice entering this data into your calculator and creating a scatter plot. Now, on the website, I have linked this calculator sheet for you to use. And if you look on here to get to scatter plots, you do stat edit, you're going to enter data into list 1 and list 2 and make sure stat plot 1 is on. And when you do that, you can kind of choose the data that's being displayed, and you're going to press zoom 9 or zoom stat, and it will create that scatter plot for you, as well as directions for fitting a regression and displaying a regression are also in there. But that's basically just going to your y equals and editing that. Okay, so make sure you practice that with this data and create a scatter plot that looks something like this. Okay, learning target 3. Describe the direction, form, and strength of a relationship displayed in a scatter plot, and identify unusual features. Ladies and gentlemen, this is DUFFS. D-U-F and S. So direction, DUFFS is the acronym we use to help describe bivariate data. Direction, you have 2 options, and that is also in our guide that I will be giving to you. And I'll go ahead and pull that baby up. Where is that thing? I'll have to do some digging. I'm not sure exactly where that is. That's right, but direction is positive or negative. Okay, and that has to do with positive slope or negative slope, positive correlation, negative correlation. Unusual features. Okay, that's going to be gaps, clusters, outliers. Form is the shape, kind of like what pattern are these lines following, and you really have a lot of options. You have linear, and that's kind of what we would expect to see, but it's also possible to have nonlinear data, and that nonlinear data could look like quadratic, but most data is probably not quadratic. It's more likely following some sort of a square root function or logarithmic or exponential. So there are lots of other non-linear type data that the data could be producing, and I would not be the least bit surprised if that was one of the that is form. I would not be the least bit surprised if that was one of the questions on the test. And strength is the last one. So the strength is really just kind of dependent upon R. R is our correlation coefficient. We're going to go over that in just a minute. But basically, if you have an R value, so I'm just going to kind of graph the number line here. This is the easiest way to convey it this is 0, 0.5, and 1, negative 0.5, and negative 1. Weak correlation is right here. This would be weak. Between here and 0.8. This is moderately strong. And between 0.8 and 1, that tiny little segment is strong correlation. Okay? And moderately strong can also be seen. This is negative 0.8 in this range, and strong can also be seen in this tiny range. So put algebraically, that would be the absolute value of r if that is the distance, is basically, if the absolute value of r is less than 0.5 away, this is going to be weak. If r is between, I don't think that really matters a whole lot there, but and greater than 0.5, that's moderately strong. And if r is less than 1, less than or equal to 1, and greater than 0.8, we'll call that strong. Okay, so this is how you describe a graph. It's also coincidentally exactly how we interpret r. So let's take a look at this really fast. Interpreting the correlation coefficient. R has lots of information kind of in the number itself. It's always a number that is between 0 and 1 as stated. The correlation coefficient, this is lowercase r, okay? R squared is called the coefficient of determination. So this is what positive correlation looks like, and it doesn't look like it's super strong correlation here. You can go to the Guess That Correlation website. That's you can probably, I can't remember if I linked it on my website, I probably did, but you can guess correlation and try and, that might be a good practice for understanding. Here's negative correlation. There seems to be a trend downward. You can kind of see a tighter pattern and it loosens up a little bit. And no correlation means as one variable increases or changes, the other variable doesn't really change at all. So there's no pattern in how the variables affect each other. Okay? So this is how you interpret. This is kind of like the formula for interpreting a correlation coefficient. There is a weak, moderate, strong, and then you say positive or negative linear relationship between the explanatory variable and the response variable. So let's take a look. For our height and arm span prediction, we got an R value of 0.95. So an R value, or 0.959. So if we got an R value of 0.95, I would say since that is greater than 0.8, we have a strong, it's slanted upwards, positive linear relationship between height and arm span. There is a strong positive linear relationship between height and arm span. Bingo. That's what that means. Super. Correlation coefficient on a roll. How are we doing over here? I think we're doing good. And all of those are present, right? Directions in there. The only thing that is not, I guess, is the unusual features. Form, strength. Okay. So we're going to revisit this picture in a bit, but this is kind of like the main idea of how outliers are going to affect your. So I want you to imagine that we only had this this little cluster, and all these other lettered points have been removed, and this was our main I guess, this is our main cluster of data. And we fit a linear regression, or a least squared regression line, to this data. Okay, so all of these points are going to change that line. Imagine the dotted line was fit before these points were added. So let's say we only added point A. Point A, is not currently, so it's all based upon, R is all based upon basically kind of the location of X and the location of, or X bar and the location of Y bar. And that is this point right here, X bar, Y bar currently. That is X bar, Y bar. So basically when we add point A, it's kind of in line, right? It's not going to help us form a relationship between the data. In fact, since it's in the same roughly region as our data and it's way far over here, it doesn't look like our X variable has a particularly strong relationship just on this pod of data if we add point A. So that's going to probably decrease our correlation coefficient because it doesn't look like we have a strong pattern, and it's the same thing with B. Okay, it's away from X bar, Y bar, which means it's not, hasn't really gone up or down, so it's not really helping our correlation. Now, the further away that is, the less it helps. So we call that kind of leverage in this case, or influence. So the further away it is from X bar, Y bar, then the more it's going to change our attributes about our regression line. Okay, so yeah, that's good. But it can also be the case that when you have an outlier that is in line with the regression that you have fit, if you had a low correlation before, like if you just had this pot of points, it's not super obvious that you have an upward pattern, but if you add point E, it's like, oh my gosh, it's directly in line. That is going to strengthen your correlation coefficient because this point has an extreme amount of influence as it is very far, or far relative to the pod, away from X bar, Y bar. So lots of influences is going to strengthen our R value because it's now we're thinking, oh my gosh, is this pattern actually correct? Well, when we go way out here, it's still in line, so this strengthens our R value. Points C and D are going to decrease our R value. That's not convincing that our regression line is actually going where it says it is. So that's going to decrease R quite a bit. And we'll go over this one more time in a bit. But yeah, so basically if you have a point that is far away from X bar, Y bar and in line, that's going to increase your R, and everything else is going to kind of mess with it. When you're far away from the line, that can really cause R to decrease. So lines that are perfectly in, like dots that are perfectly in a line, are going to have an R value of 1. And as you slowly, if they're kind of tight like this but scattered a little bit, it's going to be a very high R value. It's when you get points that look like, that's going to be something like a low R value. Super. Okay, distinguish correlation from causation. As a young adult, Mr. Slagle noticed that many successful people drove large SUVs. Mr. Slagle decides to purchase a large SUV in order to become successful. So, yeah, it didn't work out. I'm just kidding. I'm doing all right. But the whole idea here is, no, you can't go out and purchase, success. So the way that you argue this is just know, basically all you have to know is that, so although there is, maybe there's a strong association, although there is, or maybe, although there may be a strong association between success and SUV ownership. I will say financial success. We should not conclude, we cannot conclude that owning an SUV causes success. In fact, I might even argue the opposite, right? It's probably more likely that people that are really successful are more likely to purchase really nice things, but not the other way around. So you can't say which one causes what, or if they have any effect at all. Both of those two variables could in fact be related to a third variable, like hard work or something along those lines, or lots of kids. I don't know. Just a thought. This is actually my car, though. I just want to let you guys know that. Okay, perfect. What else was I going to say here? I thought there was something else I was missing. Hopefully I remember. It's going to... we're going to move on. Make predictions using the regression lines. Keep in mind dangers of extrapolation. All right, let's take a look here. So one thing that's really important to notice is if x in this case is our explanatory variable, if we have a regression model like this, we can only use this, even though in algebra you could plug in for x and y and solve, in statistics, since we, I'd like to go back actually really quick, talk about something. We talked about a scatter plot. Yeah. So in statistics, we, I have to delete that one. Whoops. What the regression line does for us, the regression line is the line, it's called the least squares regression line. And what it does is it takes all these distances for every possible line that could be constructed, and it takes all these little distances and squares all of them. So what the least squares regression line is it's the line that that minimizes the total area of all of these all of these squares. So you could draw a line up here, but the area from the data would be, the difference would be, it'd be huge, right? So we're calling this the least squares regression line, but we have done so based on we've minimized effectively the distance in arm span. We're looking at the vertical distance, not the horizontal distance between those points. So what I'm barking at here is you can only use height. In this case, you can only use height to predict arm span. You cannot go the other way around with this equation. You'd have to recalculate the regression model in order to do that, and put arm span as the explanatory variable, and you would get a different equation. Okay, so let's go ahead and sometimes when you see a regression model, so this is from Staplets, but a lot of times it's going to spit out something like this, and we'll see one like that a little bit later. Just know that here is my slope. My slope, it'll say coefficient. The constant is your y-intercept. And the one attached to x is your slope, or rather it'll display the variable in the chart down here. So that's your slope. All right, so let's take a look here. It's going to ask you to say, it'll say something like predict the arm span for someone 68 inches tall. Okay, if you're going to do that and you need to show your work by hand, there's two ways that you can write it. You can write it as y hat, or you may see it written as arm span hat. What the hat means, hat just means predicted. Okay, so it's just saying we're going to go ahead and use our model to predict the arm span for someone that is 68 inches tall. Go ahead and look through the list. There is nobody in the list that is 68 inches tall. But since 68, we measured something that was lower than 68, and we measured something that was higher than 68. 68 is a plausible value that our data set could represent, So it would not be unusual for us, like if we were to sample more people from this population, if we had someone that was 68 inches tall, that's believable. So the other way, the easier way to write it is just say y hat equals, and you're going to plug in for x the height that you're given, which is 68 inches. So negative 5.5788 plus 1.1407, and then for x we plug in 68. And if you do your math here, you get y hat, the predicted arm span for someone that is 68 inches tall, is 67.97 rounded inches. Now the faster way to do this is when you get your linear regression from your calculator, and I'll go over how to do that in just a minute, is you can go to on your calculator, go to y equals and plug this equation in, and then on your home screen you should be able to say, if you plug that in for y1, you should be able to say y1 parentheses and then plug in 68, and we'll do all this math for you very quickly. You may have a problem that asks you multiple questions about a linear regression, so having that might be a good thing for you. Okay, next is predict the arm span for a 6'8" NBA player. Okay, now this is a problem. Okay, we shouldn't is the correct answer here. Okay, I'm going to underline that, and let's go ahead and make this large again. We should, apologize. We should not do that in this case. The reason we shouldn't, 80 inches, that is 6'8", 80 inches is outside the scope of our data set for height. Okay, we didn't measure anyone that was even close, or kind of close. 75 is pretty close, but we didn't measure anyone that was 80 inches tall. So if we had, we basically, the whole idea here is this is extrapolation, right? And this is dangerous because the regression model may not be appropriate for heights in this range. We don't know what the model is going to behave like when people are 80 inches tall. Maybe a linear model isn't the best model, and there's something else that we should be using. So it's extrapolating when you're trying to take a guess outside the range of your data, and that's the big picture that you need. So we shouldn't be making guesses outside of the data that we collected. Okay, calculate and interpret a residual. I did not do that on here, so we're going to do that now. Let's take a look. So the formula for a residual is y minus y hat. So it's, I guess, what I taught you in class. A residual is equal to AP, A minus P, which is actual minus predicted. So let's go ahead and let's calculate the residual for this data point right here. That is whoever this person was. I'm not sure who that is, but that's what we're looking for. So it's the actual minus predicted. That means that any point that is above the line should give us back a positive residual. So what the least squared regression line does is it minimizes the sum of all of the residuals squared, and that's where we were drawing those squares. So basically what we're doing to calculate the residual, well, first we know the actual height of, we know the actual arm span for someone that is 75 inches tall. Their arm span, at least for this person, was 78 inches, but we don't know what our model predicts. I do know that our model will predict less. So what we have to do, I've plugged it into my calculator here, and so since I already have the equation in my calculator, I can just type y1 of, and then I plug in 75, the height that we're using to predict, and I get a predicted value from my calculator of 75.973. So we do the actual, which is 78. 78 is the actual arm span for y. Remember, this is y, this is x. 78 minus 75.97, which gives us a residual of 2.03. So what does this value mean? In red, this means the actual arm span was, I will say, actual arm span of this individual was 2.03 inches larger than what our regression line predicted with height equals predicted, I get it predicted for a 75-inch tall person. Perfect. Okay, so let's take a look. I want you guys to practice this one on your own. Calculate the residual for this person right here. All right. So you're going to have to find that person on the graph. Someone that is 69 inches tall. That's going to be right in the middle here. Looks like that data point. So that's our residual. The residual is going to be negative. We do actual minus predicted for the arm span. So that is going to be, the resid for this person is y minus y hat, which is 67.5 minus 69.13 means we get a residual of negative 1.63 inches. I put inches at the top one? I did not. So this is 2.03 inches as well. Great. So yeah, so basically in this case, the line over approximated, and in this case, the line under approximated the value. Okay, so those are some other vocabulary words you can use for that situation. 9, interpret the slope and y-intercept of a regression line. Interpret just means explain in the context that anyone could understand. Okay, let's go ahead and do the y-intercept first. So this is our y-intercept. And the y-intercept, remember, is when x equals 0. When x equals 0, x, remember, is our height. So this would mean, it really has no appropriate context, but it would mean that if someone was 0 inches tall, they are predicted to have an arm span of negative 9.5788 inches. Okay, so this is not appropriate, of course. This is not logical. It's not appropriate. It does not work for the context of our problem for multiple reasons. You can't have someone that's 0 inches tall. I mean, Ant-Man gets close, but I wonder what his arm span would be comparable. Okay, let's go ahead and take a look. Slope. Now this one we can. This is appropriate. So slope, remember, is rise over run. Our vertical is arm span. Our horizontal is height. And it's change. It's the change in y over the change in x. Well, how do we write this as a fraction? We write it as 1.14 over 1. So change in y over change in x. So this is delta arm span. This is delta height, change in height. So basically, for every inch change in height, we predict arm span will increase approximately 1.14 inches. There you go. Slope interpretation done. I believe the slope y-intercept interpretation, as well as the a couple other of them, are also, they will be included on the class website. You should have your interpretation sheet pulled up before you take the exam. Okay, determine the equation of the least squares regression line using technology or a computer. Real simple. All you have to do is go to your list. Now I know you guys don't have this version of the calculator. Enter all of your one variable into list 1, all your other data into list 2, and then you get to choose which one is the explanatory and the response variable, and you get to choose your linear regression. So you enter it into lists, and then basically I think you have to go the instructions for linear regression, stat, calc, and then you choose linreg, and you could use either of them. It doesn't matter which one you use. And then it's going to spit out. I entered the data from this, so same information that we had before that I got from other websites. It gives you R, and it gives you R squared. That is on our calculator sheet here if you want to try. So make sure you practice that. Construct and interpret the residual plot to assess whether a regression model is appropriate. So to determine whether or not a regression model is appropriate, you want to see, so in order to use a regression, and this is linear or nonlinear, regression, whatever. In order to use a regression model, you want what would seem, you would want a random scattering in a residual plot. Okay, so when you see a residual plot, basically what you're doing is you're going back to this line here. You're calculating all the residuals for each point, and you're plotting them against your explanatory variable. So here we have the explanatory variable on the, here, and then you're just plotting how far away it was from the predicted line, and you should see no pattern in the plot or in the points around the line. Basically, you don't want to see some sort of pattern. And so let's take a look at some other things here. So like this one, it seems doesn't really look like there's a pattern. It kind of looks like it's, there's points down here though. There's kind of points everywhere. There's just kind of a slight gap right there. So what we're supposed to do here is first match up the residual plots with their graphs, and they look basically the same. You just kind of have to tilt your head sideways, even though that's not technically, residuals are not the distance from the line, they're the distance down, so you have to be a little careful, but the shape should kind of be the same for each. So see if you can pick that out. I'm going to go ahead and start here in a minute if you want to pause and guess. So this one should be matched up with this one. You can kind of see those 2 points. You see a little bit of a pattern there. This one is kind of a swoop down, it would appear. Yeah, and then down here in red, those two are matched up. So let's take a look at these 3 residual plots and talk about which one a line is definitely not appropriate for. I would say the one that a line is least appropriate for would be the one in blue. You would say that this has a strong negative, positive, negative pattern in the residual plot, meaning you have a cluster of points that fall below 0, a cluster of points that are above. What this means is a linear trend is not what you want for this data, and in fact there's going to be another pattern that follows this better, and we're going to go over that in the next video. This one is, this data, it appears needs to be transformed in some way. It looks like the data is kind of fanning out. So I would say a linear is probably not appropriate. I can see a tight pattern here and expand here. A linear is probably not appropriate here either, but it might be fine. So you might want to use a linear here as well, but there may be, you want to kind of alter the data and then use a linear would probably be the best answer there. And then the bottom one, this one actually looks like linear might be just fine. A linear data might be just fine. I would be curious to see and collect more data in this range as well as out beyond. If we see the pattern kind of continue out beyond, it would be pretty convincing that linear is appropriate, but you could also argue that maybe some sort of quadratic would be a better fit. It's tough to say. Okay, so it doesn't seem like this, probably this one looks like the most random scattering of points, if I had to guess, between the 3. 12, interpret the standard deviation of the residuals and R-squared, and use these values to assess how well a least squares regression line models the relationship between the 2 variables. Okay, yeah, so in this case, we need to talk about each of these individually, so I'm going to go ahead and make this a largo. This is not the example that we've been using the whole time. Basically, in this example, you have a team, and you're looking at the number of wins plotted against their attendance per game. We're trying to see if there is a trend, as in more people are likely to show up as your wins go up. Okay, so here is the standard deviation. So when you get an output like this on the exam, the only numbers that, since they've dropped units 8 and 9, that this information here is from units 8 and 9, and so you won't need to worry about that. And we never really discussed the adjusted R squared, so I would really worry about these numbers. So this is our regression line here is going to be y hat equals, or in this case, our attendance hat equals, the constant is 10,834, so 10,834 plus, there's our slope, 235x. So for basically every additional win, the line predicts you will increase attendance by about 235. So what does S mean? S means essentially, basically, when we're looking at our data, and it's the standard deviation of the residual. So for any given data point, we would expect the line to be off in its prediction by about 7,337. So for the standard deviation of our residuals, so I'll do that in blue, standard deviation of the residuals, okay, that is the actual attendance per game typically, differs from what is predicted by the regression line by about 7,377 people. So what I'd like you to imagine is so each of those is 5,000. So see the distance on here? So it's almost like there's another line. It's almost like you're imagining another line up here and down below. And basically what this is saying is your average basically your average, if we were to go and continue sampling in this range, I think we'd probably be likely to see things fall in this range in between our prediction value, within 7,000. I'm going to go ahead and erase those lines because that was just kind of a temporary. Perfect. All right, so then what does R squared mean? R squared in another color here. Let's go ahead and go back to, let's go to purple. What is R squared? R squared is this one, okay? And you can use R squared is 0.1229. You can take the square root of 0.1229 to calculate the correlation coefficient. R squared is known as the coefficient of determination. Okay, R squared is the coefficient of determination. And it kind of determines whether or not there's a relationship between the two variables and whether or not your model is appropriate. Is your model explaining enough variation? So the way we interpret this is you say about 12.29% of the variability in attendance. So in a perfect world, we would be able to, knowing the number of wins, we would be able to predict exactly what the attendance would be. However, there are a lot of other factors that are controlling the attendance here. So basically, what this is saying is, wins can only explain roughly 12% of the variation that's happening. And so that other 88% of the variation is probably coming from other factors. About 12.29% of the variability in attendance can be explained by the variability in wins, in number of wins. You could also say by our regression model with wins as our explanatory variable. Okay, so we can only explain a certain chunk of the variability in attendance using wins, not a whole lot of it. There's a bunch of other variability that's probably caused by other things. Super. So how to assess a relationship. Assess how well a least squares regression line models the relationship between the two variables. So basically, if you have an r squared of 12, that's not great. Okay, it's saying that it's not very convincing. Like, especially, I think if we were to take this data point and move it down to like right here, we'd have almost no correlation whatsoever. So this is a very influential data point on our set, as well as this, right? If we were to move this over to here, obviously we can't just move data points, but this data point has quite a bit of influence, and if it were down here, it would almost look like there's no trend at all. So basically, this is not, there doesn't appear to be a strong relationship between these. So you want a very high r squared value for it to be convincing. So an r squared value of 1 would mean the points are all lying in a perfect line, which is highly improbable. But the higher r squared is, the better it is in convincing that there is a strong relationship between these two variables. 13, describe how the least squares regression line and standard deviation of the residuals describe how the least squares regression line, standard deviation of the residual slope, y-intercept, and r are influenced by the outliers. I don't have standard deviation of residuals here, but basically I think it's going to follow pretty much exactly the correlation for the most part. So basically, let's go over. You can follow this chart and basically say everything I'm going to say. The further away, remember, the further away you get from x bar, y bar, kind of the more weight that point has on the affecting things in your graph. So point E, basically, if we were to add point E here, if this was already our predicted line with this data, point E is not going to change the slope because it's already lying on the line. And it's not going to change the y-intercept. It is going to change the correlation. And then A and B, in these cases, A is going to drastically drop that slope down because it is it wants to pull the line closer to that point and try and predict to go through. So what that's going to do is that's going to raise the y-intercept and lower the slope. If you remove these two and add B, just B, that is going to have the same effect. It's going to bring the y-intercept up, lower the slope. Point D is right on x bar, and so it's actually not really going to want to tilt the line much at all. what it's going to want to do is bring the line down. So it's going to try and it probably won't bring it down that much, but you would expect that it's actually going to change the y-intercept slightly. And then similarly, C is going to would bring that line up just a smidge. Okay, that's basically all I have for this video. A quick recap of bivariate data and linear regression in your calculator and what these numbers mean. Hopefully this is helpful. Please watch this video as we are about to go over using transformations to make predictions as well. Okay, thanks for watching, and hope you guys enjoyed. And yeah, we'll see you next time.